All right, this is part 3 of our three-part set of videos on Chapter 4 on machine learning. So far what we've talked about is an introduction to machine learning. We talked about linear regression. Then we studied maximum likelihood estimation, which was about fitting probability distributions to data. Then at the end of the last lecture, we discuss time series modeling, and in particular this autoregressive and exogenous inputs model, or ARX model, which is something that you'll use in homework 4. I'd now like to continue and finish up this set of lectures by discussing gradient descent and a brief introduction to neural networks to give you just what you need for homework 4. So let's venture forth to gradient descent. All right, so here we are in gradient descent. And gradient descent, in fact, is a topic that I could have discussed in Chapter 3 on optimization. But I would like to introduce it now because it's going to have particular relevance for neural networks and specifically training neural networks for data-driven models. So let's now take an aside and discuss this notion of gradient descent for optimizing objective functions. So here our goal is to find the minimum of a differentiable function starting from an initial guess which cannot be easily visualized. So I have some examples here of crazy objective functions that are quite complicated, and I certainly am not clever enough to visualize what these objective functions are. I'm pretty sure that they're not convex. I know they're not convex. But I would like some sort of algorithm to minimize these functions. And that algorithm is going to be called gradient descent. Let me highlight here that this is going to be an algorithm we can use to find the minimum for nonlinear programs that are not convex programs. Okay, so this is now a broader class of optimization problems that we're interested in. So the main idea of gradient descent is as follows. It's a very simple idea. And here's the high-level picture, and then we're going to go through each piece in detail. But step 1 is you make an initial guess for your minimizer. Step 2 is you compute the derivative, or the gradient, at this point. In other words, what is the slope of the objective function at the initial guess? Then you're going to move your guess in the direction of the slope, specifically in the opposite direction of the gradient. In other words, you're going to take a step that descends most steeply. Okay, take a step of steepest descent from your initial guess. Then you're going to take that step, reevaluate the derivative, compute the slope, follow the direction of the slope in a descending direction, and then you keep going and iterating, and then you stop when the slope becomes 0. And that's, in simple words, what gradient descent is. So here's an illustration so that you can visualize it and see it in graphics. So here we have an objective function, f of x. On the vertical axis we have x. On the horizontal axis we have x. On the vertical axis we have f. And imagine that our first guess is this black dot. We will compute the slope, or the gradient, at this point. And you'll note here in this picture that the slope is positive. Yeah? So it'll point in the direction of increasing x. Now, since it points in the direction of increasing x, what the algorithm says is turn 180 degrees and take one step in the direction of descent. So that's what we'll do. We'll take one step in the direction of decreasing x, and our next iterate could be this next dot, right? Then we'll evaluate the gradient there. It's still increasing. Since it's increasing, we'll step in the direction of decreasing x, and so forth. And then we keep this process going until we get to the point where the slope becomes 0 or nearly 0. And when that occurs, we know that we've satisfied the first order necessary condition, and we are at a stationary point. Okay, now what I've shown here is an example for a convex function f, and in chapter 3 we really focused on convex optimization. Now I would like to address this issue of what happens when we have a non-convex function. Gradient descent is an algorithm that we can use for non-convex functions, for general nonlinear programs that are not convex programs. Okay, so we could have a non-convex function that looks like this curvy red function here, and immediately you should notice that there's actually two local minima. One around, I don't know, x equals 3.5, and another one around x equals 9, right? Both are local minima. Because I can graph this very easily, clearly the one at x equals 9 is the global minimum. Now, we can apply our gradient descent algorithm given a certain initial guess. So imagine that I pick something like x equals 7 for my initial guess. That's that first black dot. I compute the gradient. I look at the slope. And in this case, the slope is negative. Right? So because it's negative, I'll step in the direction of increasing x. So then I'll move to the right. I compute the slope again, I keep increasing x, and I'll eventually converge to the global optimum. So here in blue, what I'm highlighting here is we might say that we happen to pick a good initial guess in the sense that we happen to pick the initial guess where gradient descent converges to the global optimum. It might be possible that we pick a different initial condition, like x equals 5, and we, so for example, we pick x equals 5, we compute the slope, it's increasing, so we move in the direction of decreasing x, and we keep going until we converge to a local minimum. And here we've converged to a local minimum. Locally it's optimal, but globally it is not, as it turns out. So you could characterize this as a bad guess in the sense that gradient descent does not converge to the global optimum, but it does converge to a local one. Okay, now bad and good are qualitative terms, and this is engineering, so let's be precise and not get too excited about these adjectives. In practice, converging to a local optimum might be excellent. You might be perfectly satisfied. Converging to a local optimum might be perfectly okay. You could be very happy to have some design that is locally optimal and that is more than sufficient for what you need in practice. So emphasizing on achieving global optima may be important or may not really be important in practice. So although I said good guess and bad guess, actually the key point in this slide is not good and bad. The key point in this slide is depending on your initial guess, you may converge to different local optima. That's the point. All right, so here's the gradient descent algorithm to summarize in one slide. You start with an initial guess, like we're showing here on the right. Then you will determine a descent direction. And you do that by computing the gradient. Here it's positive, the slope. So then we will turn 180 degrees and go downhill. Then you choose a step size for delta x. You'll take a step in the direction of decreasing x, and then you'll get to the second point. So there's your step in decreasing x, and now you're here, and then you'll recompute the gradient and keep going with this algorithm, and then you stop when you're sufficiently close to the minimum when some stopping criterion is satisfied. One good example of that would be the gradient or the slope becomes 0 or sufficiently close to 0 within some tolerance. All right, so here's some pseudocode that you could use for this. You might give an initial guess for your optimization variable. Let's call it x naught, where the subscript is your iteration number. Then you'll compute your direction, and the direction will be the negative of the gradient. So if it's a scalar function, it'd be minus f prime of x, where x is evaluated at your current iterate, x sub k in this case. Then you'll take a step which is of size h, which again is in the direction of decreasing cost. And then your update algorithm looks like x of k plus 1 equals x sub k minus h times the gradient of your objective function evaluated at your current iterate. And then you'll keep repeating this process and stop when the gradient becomes nearly 0. All right, now that's gradient descent. I think it's quite simple and intuitive to understand. We just want to float downhill in the direction of steepest descent, and we're going to progressively calculate these gradients. So that is an important backdrop to now talk about the application of neural networks, which is going to be one of the types of regression models that are typically used for forecasting purposes. In fact, you will practice using a single neuron, in fact, as a forecasting algorithm in homework 4. All right, so what is a neural network? Now, I'm not going to make any analogies with the science of how brains work. My understanding is that that's a motivation. The link is not very formal. I would rather introduce this in a mathematical way because that is much more concrete about what neural networks actually are. So here's how I suggest you understand it from the perspective of 295. A neural network is simply a nonlinear regression model. That's it. It's a mathematical model. You have an input u and output y. There's a nonlinear relationship between u and y. And importantly, and in contrast to linear regression, this type of model is usually nonlinear in theta. It's usually nonlinear in theta. So that's what's going to differentiate it between the different types of models that we've seen before. So a graph of a typical neural network looks like what we have on the left. So this is a visualization, and it's often represented by this graph. So in particular, an artificial neural network is a weighted and directed graph where the nodes we refer to as neurons. So that's the jargon of neural networks. So in the first layer, all the way on the left, we have some input data. This could be the different elements of U. And then U, okay, so that's the input layer. Let me skip the hidden layer and go to the output layer and say, from what happens in the middle, we receive an information, and the output layer will spit out the value that we're interested in forecasting or predicting. This is y. Okay. And there's two nodes here just to represent the simple idea that y could be 2 by 1, could be n by 1, it could be 1 by 1, it could be scalar. It's flexible. Okay. Now, the hidden layer is a key characteristic of a neural network. The idea here is that each of the nodes in the hidden layer we refer to as a neuron, and it receives a weighted sum of the inputs, performs some sort of math on it, performs some arithmetic. There's specifically an activation function here, and then spits out a result. And then those results go to these output nodes with some weighting, right? So that's how a neural network operates. That's high-level version, and we're really going to break it down in simple terms in these upcoming slides. So how do we use it? Well, given inputs u, we feed that into the input layer. And then it propagates through this network, does the bit of arithmetic that is visualized by this network, and then spits out a result y. So now we might ask the question, how do we train? So what we seek to do is, given training examples in the form of these pairs, so we could have m pairs where u and y are the inputs and the outputs respectively, we would like to find the parameters theta that parameterize our neural network here that best explain this data. So we're going to fit theta on this training examples. In other words, it's a curve fitting exercise. What's special about this one is just that our function has this particular form, which can be visualized by this directed graph, and there's certain connotations to what the parameters are. It turns out there'll be weights on these arrows that connect the different neurons. Now the training algorithm is going to be optimization, as we've seen before. And because it's nonlinear in the parameter vector theta, we're going to formulate a least squares type of objective function, but it's in fact going to be a nonlinear program because our parametric model is not linear in the parameters, it's nonlinear in the parameters. Now, just for background, there are different types of neural networks. 4 of them I've itemized here. So we have a feed-forward neural network, which is what's shown here and the one that we're going to focus on, which can be represented by an acyclic graph. So we can see that this is a graph, but because of the directions of the arrows, you can see that there's no loops, there's no cycles. So everything propagates from left to right. All information flows from left to right. A more advanced type of neural network is called a recurrent neural network, and this has the special defining property that there's cycles, there's loops, right? You can actually use recurrent neural networks, as it turns out, to model dynamical systems. You may have heard of deep neural networks. That's very popular these days, a lot of business applications. Here's the definition of a deep neural network. A deep neural network just means that you have more than one hidden layer. That's it. That's the definition of a deep neural network. If I draw 2 hidden layers, I am now doing deep neural network modeling. A convolutional neural network, which has been especially popular in computer vision, is one in which the operation that these nodes do is a mathematical convolution operator. Okay, so we won't focus on recurrent neural networks, we won't focus on deep neural networks, we won't focus on convolutional neural networks. We'll just focus on feed-forward networks. This is definitely the place where you need to start. And in particular, I would like to focus on a single neuron. So let's consider the example of a single neuron. This will really help us get started to understand what neural networks are about. So in the single neuron, I have some inputs, let me call them X, and associated with each of these inputs we have an arrow, an edge, and this is a weighted edge, okay, where the weights are given by W1, W2, and W3. Now what this simple graph is trying to represent is the fact that we're going to feed to this neuron, which is just some sort of function f, the weighted sum of the inputs x, which we can write mathematically as y equals f of the sum of wixi over all the i's. Okay? And I can write this in a matrix vector format here. Now in the single neuron example, the weights, or the parameters that we seek to fit, are the wi's, the weights. Okay? Now you might ask, what is this function f? In the parlance or jargon of neural networks, this is called an activation function. And there's a variety of activation functions that people use and find useful in different applications. Some are better than others in certain situations. Just to give you an idea, I'm listing some of them. You could have the identity function, which just spits back its input. The logistic function, you actually saw this when we were talking about the discrete choice models. Hyperbolic tangent, the arctangent function, the rectified linear unit has seen a lot of popularity recently. It's actually, you'll notice that the rectified linear unit is the identity function, except when x is negative, it spits back 0. Okay. All right. Now there's many considerations to consider when picking an activation function. You might think about, what does the nonlinearity look like? Is the function continuous? Is it differentiable? What is the range? For example, the logistic function will give you values only between 0 and 1. The identity function can give you values from -infinity to +infinity, etc. All right. So let's consider the problem of training a single neuron with one training example. And to make this concrete, we're going to consider, just for fun, the hyperbolic tangent activation function. Okay? So our nonlinear regression model, which turns out to be a single neuron, is going to be y equals tan h w transpose x. I give you one training example, x1, y1, and what you now must do is find the best values for w, vector w, 3 by 1 vector, which fit this training example. Right? Now to do this, we can formulate an optimization problem. Namely, we're going to use nonlinear least squares. So what I'm going to do is take the error, or the residual, between what my data says y should be and what my model says y should be, square it, multiply it by 1/2 for convenience, and then I would like to find the value of w that minimizes that objective function. Okay, so you recognize what's in the brackets as this concept of a residual, and what I want to highlight here is f is nonlinear in w. That is why we call it a nonlinear least squares problem. So generally speaking, this is not a convex problem. This is not a convex optimization problem. So because of that, the tool that is typically used is gradient descent, hence why I wanted to briefly introduce gradient descent. So the algorithm to solve this nonlinear least squares problem is going to look like the typical gradient descent algorithm. If I have a current iteration, if at the current iteration I have a value for w and we call it w superscript k, what I'm going to do is evaluate the gradient of j with respect to w at this current iterate. Then I'll take a step in a direction opposite of that gradient, and the step size is gamma. And that is going to be the algorithm for which I define the next value of w. Now, gamma is the step size. And again, in the jargon of neural networks and machine learning and so forth, sometimes they call this a learning rate, but it's just a step size in gradient descent. So this is all pretty straightforward. The hard work is really in computing the gradient partial j partial w. And note, this is 3 by 1 because w is a vector which includes w1, w2, and w3. Right? So now what I want to focus on is the fact that training is basically about computing this gradient partial j partial w. Now, in what I'm going to show you next, I'm basically going to set up the very famous backpropagation algorithm, which will apply when you have multiple layers. Because we're only going to talk about a single neuron, we won't get all the way to the backpropagation algorithm, but what I'm going to show you next is going to give you the essential ingredients to understand it. Okay, so here again I have my single neuron, I have my nonlinear least squares objective function, and now I'm going to define a few things for convenience. So for convenience, I'm going to define the error as delta. We also called this the residual before, which is going to be y minus f of w transpose x for my one training example here. Okay. And then for convenience, I'm also going to define the weighted sum as z. Okay, so z will be w transpose x. This is just for notational convenience. All right. So with that, we have the following. My cost function can be computed as follows. J is 1/2 delta squared, and delta is y1 minus f of z, and then z is w transpose x. So you can see I've got this nested, kind of layered way to compute my cost. All right, now let's focus on the gradient, partial j, partial w. The secret here is chain rule. That's it. We're just going to apply chain rule. And because I've defined this notation in a particular way, we can unravel this in nice bite-sized pieces. So using chain rule, we can express partial j partial w as partial j partial delta times partial delta partial f partial z times partial z partial w. And with this decomposition, now I can focus on computing the gradients for each of these four terms here. So for example, partial j partial delta is just the derivative of this first bullet point over here. We can see that's delta. Partial delta partial f is just -1. We'll just get -1 to pop out. Partial f, partial z. So f is this hyperbolic tangent. Remember that from the last slide. So the derivative of f with respect to z is just f prime of z. And it turns out that the derivative of the hyperbolic tangent is 1 minus tan h squared. So I'm just writing that out. And then partial z, partial w, here I have z, is just the 3×1 vector x. Right? So now with this, I can take all these three components, multiply them together, and voila, I have my formula for partial j, partial w. So now what I've done is just written this all out and written out my gradient update iteration, my gradient descent iterations as follows. So we have wk plus 1 equals wk plus gamma times times the negative of the gradient here. Okay, so the first term in brackets represents delta. -1 converts this minus sign into a plus sign. Then I have f prime. I'm just writing as f prime here. And then partial z, partial w is this matrix multiplication with a 3×1 column vector x. And here we have our algorithm that we iterate to fit the weights with gradient descent. Okay, so that was training with one example on a single neuron. And this is exactly how you start if you want to understand how to do training with neural networks. So let's now take a step forward and ask what happens when you want to train with multiple examples. So you have multiple data pairs. So here now we're postulating that we have, we suppose that we have m examples in terms of these pairs. And now what I'm going to do is the typical least squares objective, where I'm going to minimize the sum of the square residuals. Right? So the key thing that changed here is the summation over I, and now these superscripts on y and x are i's here. We go through a similar process. We define for convenience this error delta superscript I, which is a residual. And now we focus on the gradient and use chain rule. Now, because we have multiple training examples, we're going to have this summation here. And just as before, we can focus on evaluating the gradient with respect to each of these terms. So we can just break that out. And then when we multiply it all together, we now have this update law. Okay, so I know this may seem like a lot of really, really small details pieced together, and indeed it is. I really wanted to go through these small details one by one so that you can see how it's all assembled together. And in the end, you get what looks like a relatively complex formula, which takes a little bit of work to derive, but the concepts are in fact quite straightforward. To review, all we did was gradient descent and applying chain rule. That is it. So in homework 4, what you're required to do is to build a forecasting algorithm based off a single neuron. That looks just like this picture here. Now, I'm going to stop here on neural networks, and I am not going to lecture more on how you expand this out to a full network. But if you're anxious because I haven't gotten that far, I'll just mention the following. That now that you understand how to do training with a single neuron and with multiple training examples, it is really just a matter of good bookkeeping and being very careful with your notation to expand this out to the full network. And to expand that out to the full network, you will arrive at the typical backpropagation algorithm. In my opinion, I find that when you expand this out to the full network, it gets pretty hairy in terms of just tracking all the mathematics. And it's actually not too insightful beyond what you can understand well with a single neuron example, which is quite simpler. And of course, there's a lot of open source software tools that'll do this training for you. So to summarize here, training of a neural network is a nonlinear regression model in contrast to the linear regression models that we studied before. Because it's nonlinear in theta, we generally do not have convex or even quadratic programs that we can solve to train these networks. But we can still form this least squares style of objective function shown here, and then use gradient descent to update these parameters. So with that, that closes my set of lectures on machine learning. Thank you.